Okay, so the next speaker is Arthur HUTSALYUK. Good.
Okay, should I start?
And you will talk about generation function and full counting statistic in integrable system? Indeed?
Yeah. So basically I would talk about generation function, but for those people who don't like generation function per se, you can use word full counting statistic, it's literally the same. So, okay, let us start with very boring introduction about general stuff, general algebraic beta ansatz. It's a few minutes relatively boring stuff, and next, okay, we will turn to more interesting things. So, okay, very general notation about algebraic beta ansatz. We have monodromy matrix and use very standard notation, A, B, C, D. Technically, the method should work for any system with finite dimensional representation, but let us start from keeping in mind, for simplicity, XXX or XXZ spin chain. Okay, then we define the transfer matrix in a pretty standard way. So this is just operator A plus D. What else we did? Okay, basically, so what is the next question? If for our system there exists vacuum such that action of operator C on this vacuum is given 0, then algebraic beta ansatz for our integrable system could be built. And okay, beta ansatz could be built in the following way. So we have some transfer matrix. It acts on beta vector that depends on set of spectral parameter U. And it's give just eigenvalue of our, so eigenvalue we will denote by lambda. It depends on set of spectral parameter. And we have that, okay, so U is just beta vector. And it's given by very simple way, just monomial of B operator, B U1, UN, acting on vacuum. Technically U1, UM. So what is NM here? M is just number of magnons, and it's less equal. It's actually could be anything between 0 and system size. And in order to this be true, we should also keep in mind that certain restriction for rapidity should exist. It's called beta equations. I don't know, probably let's just write in general form. Beta equations for uj, u equals 0, for j equal 1m. Okay, so far so good. I don't think there are any question. It's just usual algebraic beta ansatz, how to diagonalize usual matrix. Well, okay, but usually we just don't want to very abstract question about spectrum. We want a little bit more. And one of basic questions that people would like to know is how to compute expectation value of local operators. Okay, then we need to express local operators in terms of some algebraic beta ansatz entity in this quantum inverse problem that for any local operator x that acts inside J, the following formula exists. Trace 0. At point 0. So what formula says that if we want to have operator that acts at point J, we should basically consider trace of this operator acting in the auxiliary space, multiply it by monodromy matrix with with 0 spectral parameter, and consider here and make these sandwiches out of 2 transfer matrices taken at point 0. Very standard stuff. So let us now just write the formula that we will need in the future. I believe Tj 0, T, oh sorry, J minus 1, 0, Tj 0, it's sigma Z, J, and sigma plus minus would be Tj minus 1, 0, C or B correspondingly 0, Tj 0. Here G is just a power. Any question to this moment? I think no. Okay. Now a little bit more complicated stuff, but still very simple. Let us consider not usual transfer matrix, but twisted transfer matrix. With some, so what is twist? Let us consider some diagonal matrix K, and it would have following parameters K, kappa, and tilde kappa. Then we can define transfer matrix in the following way. It would be given like this. So what we, and we would have here, maybe it should be bigger, subscript K, sorry. Here, yeah, sorry.
So in some sense you are in fundamental representation for the T and its product of...
Yeah, okay, so as I say, we keep in mind that for simplicity, I define now everything for xxx/xxz spin chain. Technically, of course, inverse problem could be solved for more complicated problem, but the only restriction for us probably would be finite dimensional representation. Okay, maybe there are some exotic representations where I could be not used to. But let's keep in mind the simplest problem. So, okay. So far, let's just define transfer matrix with a just diagonal twist. So what we know in the result? We know that new transfer matrix, sorry, it's tk lambda. It's again, okay, whether it's usual transfer matrix, whether a twist is transfer matrix, it's commuted with itself. This means that this is generation function for some set of commuting quantities, for some integrals of motion. Okay, but what we know, however, that usual and twisted transfer matrix does not commute. That means that these matrices have different bases, and we would use this. However, as the other hand, I already mentioned they have different bases. Indeed, matrix Tk could be diagonalized in absolutely the same way. So let me just write for reference. We would need it too in some way. I everybody add this subscript K in order to not forget that something dependent on twist. And what exactly depends on twist? Only beta equations depends on twist. Probably I would like to not to write them explicitly for now because we don't need it. Again, the situation is the same. We have the system of M equation where M is number of magnons and M could be anything between 0 and n. And we know that particular solution of this beta equation, if we substitute it into particular set of U, we substitute into our beta vector and we get particular beta vector. And this way we can reproduce all bases. More or less completeness of bases is proven only for very particular cases like fundamental spin chain. Even there I'm not sure that everything is rigorously proven, but more or less we know that it's good checked fact. Okay, now let's try to use this knowledge for something. Whether we have everything. Okay, sorry, I forgot, of course, about one technical moment. One more moment. It's good to have beta vector itself. Okay, we have, for example, even dual beta vector. But if we want to compute something, it would be very useful to know at least, let's say, overlap between few beta vectors. And it would be also good to know whether, for example, if both of them are, if both vectors are eigenvector of the transfer matrix, whether what happens in this way. And the answer is following. Technically, we can compute overlap between arbitrary vector, beta vector, and the beta vector that is eigenvector of the transfer matrix. And moreover, what is even more important for us, we can compute overlap between usual beta vector and beta vector of twisted transfer matrix. The answer is, well, it's a little bit complicated. We don't need it explicitly. What we know is that it's given by some determinant. So call it some node determinant. Like, there are some more or less important prefactors. There is some structure of the node determinant, but what is most important for us is that there is some structure of the answer, and it's structure good enough for the following reason. At least for us, it would be important for the following reason. Let's consider a situation when number of magnons M is large. Number of magnons M is large, and the system size is large. Then, of course, we would like to, large means technically to infinity, but M over N is fixed to some value. So, such a limit usually possible in case of Slav node determinant, and for us it's important that thermodynamic limit exists. And this is already open to us way to apply this, all this machinery to something useful. In particular, so let us consider a very specific twist. You would see now what I want to say of this type. Then let us write explicitly this transfer matrix. This transfer matrix is equal A plus D e to the beta. Oh, sorry, K, not kappa. At the first hand, at the first side, we know this. At the other side, we know such an inverse problem. So let us try now to start from here. Let us compute this operator, where SZ let's even put L here explicitly, sigma Z J. It's L. So we can write in the following way, obviously. Even more. We want this one. And we know that this is product from J plus L. I believe it's A plus D plus e to the power beta A minus D. Multiplied by t to the power minus L0. So where it's come from? Okay, so first of all, of course, all this stuff could be linearized at something like cos hyperbolic beta plus sin hyperbolic beta, sigma Zj. This is just, this particular exponent can be linearized in this obvious way. And next we use this quantum inverse problem. And we use the following fact. For example, just very simple example, sigma 1z, sigma 2z. We use the fact that this J are organized in such a way that, let's try, for example, sigma 1 and sigma 2. So here, according to the power, T0 goes in the power 0. Here, T goes to the power 1. It's just for first side. And then for the second side, T minus 1, 0, A minus D, T minus 2, 0. So, as you see, everything in between always cancel out. The first power is just 1. So we get technically this formula. Okay. And next, one more step that we need.
Sorry, what is small l? It's just some random site.
Yeah, it's number of sites, yes.
Total number of sites.
Yes, no, not total number of sites of system, but total length of this operator.
Yes.
I don't know. Can you see? Maybe I wrote too small. And okay, probably here I'm not sure that. Oh, of course. Sorry. I take for let's write here CS. CS, I mean cosinus beta and sinh beta. So far, so good. And at the very end, this is a plus, so it's something like a plus d e to the power beta. After we simplify, to the power, all arguments at power 0, with argument 0, to the power a, lt minus l. Okay, so as first point, we know this. And now let us try to calculate expectation value of our operator, of our exponent. So we have a beta vector parameterized by set u. Next we have this expectation value as sigma lz. And next so we use three facts. First of all, we use the fact that this is nothing but twisted transfer matrix, tk. To the tk in 0 to the power a. And next, we use completeness of beta basis. And voila. Basically, we have everything that we want. Whereas for completeness for beta basis, we of course use resolution of unity, 1 as sum over all solution of twisted beta equations. Or twisted beta states, sorry. I lost normalization factor, thank you. So this k is left and right. Sum over all solution v, sum over minus 0, u. And next, we know very simple things. This would act like any eigenvalue, like if this is eigenvector, so beta vector where we satisfy set of solution of the beta equation, then this vector is eigenvector for this twisted transfer matrix. And this vector is eigenvector for this transfer matrix. Of course, here summation is taken exactly over all possible solution of beta equation, or rather all admissible solution of beta equation. And of course, u are eigenvectors, because by construction, we are interested of expectation value of this operator between eigenstates. So at the very end, we come to the so-called Fox factor expansion. Okay, basically, the answer would look like this. At this point, lambda kappa over lambda at 0 v 0 u to the power l. And this is like very simple, let's say very simple trick so far, and the simplification is following. Instead of quantities that we just don't know how to compute, we obtain this sum where every term is exactly clear. This is, as I mentioned already, some non-determinant with some prefactors, of course. Okay, here, of course, I forget about normalization. That is Godin determinant. And here are eigenvalues that, of course, we know how to compute. The only simplifications that we get in response is summation over all possible solutions of beta equations. And then it's a separate problem how to compute this sum efficiently. And there was intensive progress in this direction. It was developed by Leon Group, by Leon Group. Who else should be mentioned? Of course, Karol Kozlowski and Frank German. And okay, so there is a more or less efficient method how to fix, at least at the first goal that would be here. We know that at the very end, this correlation function behaves in the following way. Sorry, it's raise the L. We want to know how to this behave with respect to the system size. And usually not the system, sorry, not system size, but this distance L. And usually the answer has this structure. So if model is massive, then of course there will be this exponent with some correlation and L psi, yes. And if it's massless model, there will be just power law decay. But okay, this is a well-known result. Now let's try to make it a little bit more complicated. Let's try to compute operator sigma x L. With sigma x L, the situation is a little bit more complicated. Just how much? Okay. With this situation, everything is more complicated. Since if we just try to use some express everything in terms of transfer matrices, it will be not so easy. However, let's try now even more difficult game. Let's introduce non-diagonal twist. Surprisingly, now we can build transfer matrix again, just by analogy, pure analogy so far. Okay, 2T. Okay, the new transfer matrix technically is bad. The problem is that it's technically every element of this transfer matrix contains so let's just do the following trick first of all. Let's denote T tilde. Let's we extract from this K some diagonal path, and something and everything non-diagonal would go into the definition of new transfer matrix T tilde. And then we know that every matrix element of Tj is some linear combination of all of A with some coefficient plus B with some coefficients plus C with some coefficients plus D with some coefficient. And at first glance, it looks like diagonalize this transfer matrix would be an impossible problem, since trace of this transfer matrix, even trace, would contain all A, B, C, D. Moreover, element T1, 2 of this transfer matrix also depends on A, B, C, D. So technically there is no vacuum too. So what we can do in exchange? However, it happens that such transfer matrix could be diagonalizable. This is exactly what call it modified algebraic beta ansatz, and I believe that previous talk was about this. So very general idea. Actually, idea is almost the same. Let's build new beta vector. This new beta vector would be just a monomial. Sorry, now let's use notation T tilde 1, 2, 1, T tilde, let's say M for beginning, 1, 2, M, and they act on the same vacuum as before. So very naive attempt to build beta vector by the old way. And it happens that this beta vector, U, would be indeed eigenvalue of transfer matrix under the certain condition. Let's just keep this K, K. We are under K, I mean our non-diagonal twist. Yeah, sorry. Let's just lambda UK, U. There are, however, conditions. First of all, again, we should have beta equations. Now it would be modified beta equation. And one more condition. Now we cannot take arbitrary number of magnons here. Number of magnons on number of beta rapidities is fixed. It depends on the specific representation. For XXZ X or XXZ model, actually we should, with this parameterization, I should restrict myself to XXX model. With this parameterization, m would be equal n. So number of magnons in our model coincides with the number of sites. Okay, we have some problems, but more or less we know how to diagonalize this transfer matrix. The question now whether we could compute, for example, like it was before. And it happens that yes, and it was done in 2021 by a group of, I think, paper of Pimenta, Billiard, Slavnov. And the answer is again given by some Slavnov determinant, modified, of course, Slavnov determinant. It's again, it's too much, not enough time to give details, but let's say that some compact representation for this overlap exists. There is again some prefactor, but overlap exists. And now let us use our old trick. So let us write here transfer matrix explicitly. So at one side, transfer matrix is given by following. It's just T tilde D11 plus T tilde D22. However, let's express this. Sorry. D here, of course, not the same D as was there. It's just some diagonal twist, let's say. D tilde, I don't know. Hopefully it doesn't create too much confusion. That D here is just a diagonal twist. So what is important here is that okay, of course, these coefficients depends on specific twist, on specific details of twist. And technically speaking, this twist is as absolutely arbitrary, at least in x66 case. And I would use very simple parameterization. Then it's easy to see. The transfer matrix would be given by following construction. Well, it's not easy to see, but it could be checked, more or less. Again, now let us use old trick. So we won't compute this operator. So then everything by analogy. So what is this? Cos beta identity plus sin hyperbolic beta sigma xj product. And next we use our old inverse problem. Because our old inverse problem, we know how to rewrite this, and both unity and sigma x operator via A, B, C, D. Okay, sigma x operator is of course just a linear combination B plus C. So at the very end, we arrive to the very simple statement. Everything like before. And now we use absolutely the same method. And okay, at the very end, instead of just rewriting everything, I just repeat you to the old formula. Where, of course, here should be replaced this twist by non-diagonal twist, and this eigenvalue by this new eigenvalue. And of course, overlap should be replaced by new overlap. So this is basically trick how to compute this generation function for Sx operator. Of course, it's absolutely clear that is absolutely similar manner. We can do it for Sy and for combination of Xx for Sy whatever. We have large degree of freedom here, choosing all these three parameters. And okay, this problem looks like a bit ridiculous problem, but actually, since this operator is nothing but full counting statistic, it attracts some relatively major interest last year. last years, let's say. And despite this, not too much progress is known, at least for sigma z operator. There are results for free fermion XX chain by Fabian Essler in 2017. For SX operator, I believe that the only result is half. Okay, both results are half analytical, so half numerical. So for sigma z is only Fabian Essler. For sigma x, there is for massless phase CFT result by Pasquale Calabrese and Sara Murciano. Okay. More or less the story about this finished modulo the possible generalization for higher rank algebra. For higher rank algebra, non-diagonal twist is absolutely unstudied field, but diagonal twist at least is good studied field, and the results there could be obtained. Moreover, in this case, technically when we did only with diagonal operator, we are not obliged to keep fundamental representation because in some cases we don't even need inverse problem, so even more general result is obtained for full counting statistics in high rank, but only for diagonal cases. It's a result by well, it's basically result is possible as long as you have exact formula for this overlap, and they are known for SL3 and SL21 matrices, and result for this diagonal operator for diagonal elements of full counting statistics. Basically, this generation function is published in paper of me and Andriy Lyashek in 2021. Of course, in this case, this analysis become. Of course, in this case, first of all, there are not just a single. Let's say instead of SZ, we have at least, so basically number of possible operators coincide with rank of algebra, so we have two diagonal operators, and of course in this case it would be, basically it's a problem in development, but it's a separate problem to calculate long-range asymptotic, because statistical algebraic method gives you idea how to calculate generation function. How to compute asymptotic of this generation function, it's well, it's a separate problem. Okay, basically I more or less finished. I should quickly add two possible progress. So one is of idea would be, well, the few idea would be, first of all, the question whether we can generalize, at least for rational case, this method of computation full counting statistics for high rank algebras. Another case whether we could generalize it's generally for XXZ case, because technically this twist such a non-diagonal twist of general form could be taken for XXX spin model. For XXZ spin model, you can take as a diagonal, as a complete anti-diagonal twist. You cannot take a case when all 4 is not 0. So some definitely some tricks would be required here. One more possible idea would be to deal with open spin chain. One more idea, but okay. One more idea is technically absolutely obvious that here the computation is done by inserting full set of states with respect to twisted states, while external states are untwisted. We could do it absolutely vice versa. We could take external states twisted, internal states untwisted. And external state twisted, it would correspond to the very simple trick. It would correspond to just it would correspond to Hamiltonian with broken U1 symmetry. So basically usual XXZ Hamiltonian plus some very specific boundary condition. Well, specifically in sense that they would depend on spin parameters. One more idea would be, of course, here I I didn't say anything about the state. So of course I keep in mind ground state, but it can be any excited states. And technically we can use here instead of even usual state, instead of state of usual transfer matrix, state of quantum transfer matrix. And in this case we can introduce some temperature. Well, I think maybe there could be even more nice ideas, but for some moment I think I more or less.
Thank you. Any question? Yes. 1, 2.
So how about for the XYZ case?
Well, I'm not. I don't know anything about overlap of twisted and untwisted beta vectors in XYZ case. Because here is basically usual beta vector. Here is beta vectors with non-diagonal twist. I don't know whether such overlap exists in the literature.
For XYZ?
Yes. I don't think so. It's.
Oh, yeah.
Then even worse. Then even worse. You don't have too much degree of freedom there at all.
Yeah, of course you have off-diagonal twist, sigma X or sigma Y. That's the pick. Just discrete windows. Yeah, well, X, Y, Z.
So thank you for the nice talk. Just in relation to your comment on higher rank, when you said that these overlaps of like generic twisted overlaps has not been studied. So these formulas do exist within the separation of variables approach. So
Yes.
And in fact, I think most of the ingredients which you use, for example, this overlap of twisted for generic twist, this diagonal, and also there are formulas for generic twisted with diagonal. These also exist. So I think your methods are actually this general program you have outlined in combination with separation of variables would work, I think, for higher rank.
I'm not sure that I even understood how to take in the separation of variables thermodynamic limit.
Yes, indeed, that part is.
It's known at least for algebra symmetry SL2, and I think it could be alternative approach. But as far as I know, for the higher rank, they experience certain problem.
Yes, so thermodynamic limit for higher rank is not understood, but the rest of the machinery you use is there. So if that could be understood, then I think you could apply this thing.
Well, without thermodynamic limit, at best it could be used for numerical computation, but not for analytic formula of this type.
Yeah, but for SL2, even about what was present about this question of taking the determinable limit for a non-new one, even in separation of variable, it's always come back to usual TQ with, and what I know, it's 4 ground states, and probably we don't know for next states. This inhomogeneous term disappeared, so in some sense everything come back to the non-technique. And yes, I'm curious to see also what's your technique, and also improve the calculation for correlation function or other quantity. Okay, and do we have a question? So basic. So for SL3, so this same technique you say, work for SL3 is what you use. So just about the calculations for SL2, it was done by Carol and Frank.
Sorry, for SL2.
It's more about you don't speak, but about the thermodynamical limit. After they can go up to the end to sum up about all the states and their integral formulation and thermodynamical limit for your formula there, because you sum up about all the possible states.
Yes, of course. Sum up over all possible states, it's would be impossible, even numerically. Of course, they have some efficient way to distinguish which states are important. And actually, it's in algebra symmetry SL2 with diagonal case, it's almost obvious. You take here some state. You fix the state. Yes, it's just external state. It's fixed. Then okay. Basically, idea very simple. Density of states should be the same, macroscopic density of states. If it's different, these overlaps would be negligible. So these states contribute, and then you should take some summation here just over very, okay, it's still very large, but excitation of certain type. Like particle, for example, for massless case, it's particle Hall excitation near Fermi zone. This would be the modes that contribute, at least in the first order. If you want to have high orders, all possible correction, it's still everything is defined by behavior near Fermi zone. If it's finite temperature state, then the situation a bit more different. You need to formulate everything in the terms of nonlinear integral equation by Klumper. But then again, of course, summation is possible.
Okay, thanks. Other question? No, maybe we make some break and wait for next talk. Thanks.